Ladies and gentlemen, I would like to welcome you to our second edition of the Rare Earth Roundtable series. My name is Roland Gauss. I work for EIT Raw Materials, which is a large European knowledge and innovation community in critical raw materials. And this webinar is part of an innovation project financed by the European Commission. The project is called Magellan, and you can find a lot of information on the website. Now, with this roundtable, we really want to share, the objective is really to share latest developments, technological developments, but also developments in terms of the market with an interested audience, not only experts, but people that want to learn more about the situation in rare earth and the challenges and opportunities this sector is facing. Now, today we're looking in a very, very exciting topic. We're looking at the urban mine. Now, what is the urban mine? The urban mine is basically the stocks of materials, the products that surround us, and that in the future actually offer a huge potential for extraction and processing. And despite the fact that rare earth have such a large, or huge, enormous functional value for our society, as you know, you can find them all kinds of applications, as we discussed also in our last roundtable series. It's still not really recycled at scale, at least in Europe. So lots of these materials are actually lost at the end of the lifetime. So the question really is, what are the strategies to move forward? And how can we really put this urban mine at the center of a sustainable extraction and processing of such precious materials? Now, today I have a really extraordinary set of speakers here with me. We have Edoardo Righetti, who works for the Center of European Policy Studies. We have Jürgen Gassmann, Head of Magnetic Materials at Fraunhofer IWKS. We have Pierre Vyas, who is EU funding expert at Comet, a recycling company in Belgium. And we have Lukas Brandl, CEO at the Battery Lifecycle Company. And we also have with me here with us Jenny Kvetera, who's a Senior Advisor Critical Materials at EIT Raw Materials. And she will, with me together, moderate and go through this webinar. Now, as the setup of this webinar, we will have it like the last time. We'll have each of the speakers has 10 minutes to present, what they're doing and how they see the development in the urban mine and the extraction of these materials, the opportunities that come with it. And then after each intervention, after each presentation, we have 5 minutes for questions, for immediate questions, for a direct follow-up. Please use the Q&A window. There's a specific Q&A window that you can use to put your questions and put them in allocate and bring them forward so we can discuss going forward. So you have the chance to put these questions right after the talk. And at the end of after the 4 speeches, we also have some time left for further discussion. Now, I'm very excited to hand over to Edoardo. Please share with us your view on the potential of the urban mine. Edoardo, can you share your
Sure.
Over to you.
Thank you very much, Roland. You should be able to see my slides in a second. All right. Hopefully you see my slides now.
We are not. Yeah, now we're seeing it. Thanks very much.
All right. Fantastic. So thank you very much, Roland, indeed, for the introduction and for the kind invitation. Indeed, as you already mentioned, I'm Edoardo Righetti, and I'm a researcher at the Center for European Policy Studies, CEPS for short. And indeed, I will be presenting a little bit the work that we have done on rare earth and rare earth permanent magnets recycling over the last couple of years. Before I do that, let me maybe just spend quickly a couple of words about my organization first. So CEPS is an independent Brussels-based think tank, meaning we're essentially a policy-oriented research institute covering the whole spectrum of EU affairs. And our primary goal is to inform and orient the policymaking process, right? So we do so primarily via our own research, but also by providing a platform for our partners to engage and discuss on policy-relevant topics. So that's what we do. what does a think tank then have to do with permanent magnets recycling, you might ask? Well, since 2021, SEPS has been involved in EIT raw material funded project named INSPIRES, which is the acronym of the very long title you see up there, whose main objective is essentially to sustain the secondary supply of rare earth within the EU by innovating and possibly scaling a hydrogen-based recycling process for rare earth permanent magnets called HPMS. The focus is particularly on the Slovenian region, where several of the project partners are located and where there's traditionally a strong presence of magnets, of the magnets industry. And the target is particularly on home appliances, which includes, for instance, washing machines, tumble dryers, and similar devices. In that context, our role was to assess a little bit the potential of permanent magnets recycling in the EU, based on insights drawn from the project, but also from our own research and consultations. And based on that, to develop some tailored policy recommendations on how to promote establishment of recycling for permanent magnets in the EU. More specifically, our research, which actually culminated in our policy report that we published in late 2022, divided into 3 major exercises, right? So first, an overview of the rare earth and rare earth permanent magnet supply chain. So an overview of the major bottlenecks there, essentially. Then a qualitative assessment of the major barriers inhibiting recycling, permanent magnets recycling in the EU, and then a quantitative assessment on the future potential for permanent magnets recycling to cover future demands of permanent magnets within the EU. So I'll try now to quickly summarize a little bit the results of our work, which you can also find in the report itself. So starting from the market, here is a very condensed snapshot, right, of the market and the value chain overview. Just to give a very quick few sort of highlights to frame also a little bit the discussion and underline why it is actually important to have conversations like the one we're having today on this topic. First of all, permanent magnets are the largest rare earth use segment, accounting for roughly 30% of the overall market volume, a share that is actually likely to increase right in the future, particularly due to the expansion of some specific markets, for instance, those related to the green transition, right? So EVs and wind turbines. Market-wise, neodymium iron boron is the dominant magnet compound, thanks to higher performances compared to market alternatives. In terms of neodymium iron boron magnets applications, estimates again can vary quite significantly because there's a certain sort of uncertainty within the market in terms of final uses, but breakdown usually report a substantial share from from consumer electronics, but also conventional vehicles and EVs and wind turbines that again are expected to somewhat take an increasing larger share of the market. What is maybe more interesting here is that when it comes to geographical concentration of the whole value chain, and again, it's possibly not a surprise, but the value chain is very concentrated, highly concentrated in China, notably at the sort of final stages of the permanent magnets value chain, particularly permanent magnets manufacturing, where China is responsible for some 90% of production, again, depending on the estimates. And that, of course, then lead to a situation where 98% of the EU demand for these components is met by Chinese imports, reason why then it is crucial to enhance our EU recycling capabilities in this area. So provided then the recycling technologies and processes exist, and I'm sure we hear more about them in a minute from the other interventions as well, what are then the major inhibiting factors that are or might be preventing their deployment in the EU? To understand that, we carried out a number of interviews with experts from both academia and industry throughout all segments of the permanent magnets value chain. And what you see here essentially is the coded information that we received, right? So divided into 4 major categories with the frequency with which the different barriers emerged throughout our conversations. And of course, I won't have time to go through all of them, but just again to give the main highlights and mention those that really stood out. First, from a policy sort of regulatory perspective, the key issue identified was really the lack of some forms of labeling or marking requirements that would provide information, for instance, on the amount, on the type, on the chemical composition of magnets within the product, as well as potentially on the possible use of coatings or other chemical additives. There are information that are that are very important, particularly for some recycling processes, such as the hydrogen-based ones that require a certain level of homogeneity as a clean feedstock, let's say, for the process itself. Then on the technical side, a major barrier that emerged referred to the process of extracting the magnets from the product themselves, which is particularly for smaller application quite challenging. Magnets tend to be firmly embedded, particularly in the first fraction, often again by means of glues and other substances, and therefore extraction can be quite challenging and sometimes results in material losses. And this technical sort of challenge then reflects, of course, into the economics of the whole recycling process, because then extraction turns out to be a very time and labor intensive process and then ends up representing a major cost burden for recyclers themselves. Moving to then the recycling scenarios. Now here, we then ask ourselves, provided that these barriers were to be to some extent addressed, and we would manage to have a somewhat more or less efficient recycling system for permanent magnets, rare earth permanent magnets in the EU, what could then be the actual contribution of recycling to meet future demands, and within which timeline? And this is how the picture looks like, right? So we looked at, of course, some selected applications. Indeed, as I mentioned before, magnets and rare earth magnets are used in a huge variety of applications, so it's not necessarily super easy to intercept all of them, but I believe we managed to cover somewhere around 70% of the actual market, current market. And what you see here is essentially that recycling could potentially, based on our calculation, contribute to somewhere around 10 to 20% of overall demands of neodymium, of permanent rare earth permanent magnets, which is a relevant but not very high share, and this is predominantly due to the rapid market expansion of some product categories, particularly again electric vehicles and wind turbines, which will not be matched right away by an equivalent expansion of the stream of end-of-life applications. Right, these applications stay in the market for quite some time. But then starting from the mid-2030s, thanks to, from one side, the gradual slowdown of the demand, so the demand curve that somewhat flattens a little bit, and then at the same time, an increasing availability of end-of-life applications, recycling can potentially start to play an ever-increasing role, so much so that in 2050, we could potentially expect, again, in a very optimistic scenario, for recycling to cover even half of the demand, basically, of these magnets.
Question, Eduardo, and that's a very exciting message. So from your point, from your statistics, from your forecast, you'd see by 2050, almost half of the demand could be covered by recycling. Are you referring to the diagram on the right-hand side in the upper curve there? Could you?
Exactly. So that is a very, again, optimistic scenario, depending, of course, on the efficiency of the recycling process. So happy to go in details on the methodology, but essentially we break down the recycling process into 3 major steps, and we, based on literature and again on consultations that we have with experts from the industry, we try to define more or less what the efficiency at the different stages could be. To provide a sort of window there for a more or less optimistic scenarios, and in the most optimistic one, we could potentially cover half of the demand. Again, that's very much based on the very specific set of product categories. So yeah, and on a very specific type of magnet.
Yeah, I'm just trying to understand and make sure I understand the diagram. So it's the diagram on the right-hand side, and it's the
exactly. So on the right-hand side, you see the upper sort of line representing the most optimistic scenario. I think I might have been able to actually use the pointer there.
That would be, I think, would be good.
Okay, you should be able to see that.
It's very exciting data, and that is the top line of supply.
Exactly. Basically. So this is the most optimistic scenario. This represents the demand, and this is the theoretical recycling potential. So the overall amount of magnets reaching end of life, and the two sort of accounting for efficiency, the two more or less optimistic scenarios of secondary supply. And the bottom line is the less optimistic scenario, let's say.
Okay, very fascinating. Thanks.
Okay, no, thank you for the question. So yeah, and then again, from 2050, we could expect, or even before actually, a significant contribution of recycling. So based on, and here I somewhat close the sort of narrative on the the assessment that we made based on particularly on the assessment of the barriers, these are the recommendations that we proposed, which are somewhat self-explanatory in a way, right? So first of all, introduce labeling requirements, labeling or marking requirements on end-of-life products containing magnets, which is a little bit the conditio sine qua non if you want to create business case around recycling, right? Recyclers need information about the magnets, and they possibly need it beforehand, right? So before they actually get their hands on the magnets and dismantle the product, which is a very, as I said, consuming time and labor-consuming process. Then develop ambitious, but yet, of course, realistic and gradual recycling quotas for magnet, which is a little bit of a long-term recommendation there to create demand. Another fundamental, piece of the puzzle there, if you want to have a viable business case. Provide financial support. Again, quite straightforward, but several of these recycling operations might not yet be necessarily economically viable, particularly in the early stages. So there you might need some form of financial support. And then, of course, establish some forms of eco-design requirements to facilitate the extraction of magnets themselves. To conclude, just to say that, as I mentioned, we published the report in late 2022, and we were actually quite pleased to see that actually most of the recommendations were then taken into account to some extent by the Critical Raw Materials Act, which entered into force in May this year, with 2 specific rare earth permanent magnets related articles, which introduced both labeling and recycled content requirements on top, of course, of the broader sort of support framework for strategic projects, which include as well recycling. So that will be it from my side. Yeah, happy to take questions if any.
Thank you very much, Eduardo. Are there any questions, immediate questions?
Yes, thank you very much for the presentation. We actually have Helena Robert who raised her hand, so let's see if I can let her to ask the question. Can you talk, Helena, now?
Otherwise, you can also type the question into the Q&A, and we can read it out.
It looks like we are not hearing, so yeah, let's wait for a second. She's typing the question. So if you have any questions, please use this Q&A box. So we
yes, I did type the question, and we'll read it out. No, thanks again, Eduardo. I think for me, one of the key takeaways is that the enormous potential of the urban mine, as we're building up stocks, particularly with these new applications also coming in. Now, why can't, I mean, talking to stakeholders in China, but also in Japan, there seems to be quite an established business to close this loop. Why can't they do it? Why can we not do it so far? So I read over the years again and again, less than 1% of the rare earth materials are actually recycled in Europe. So what is the kind of for all the bottlenecks that you listed, compared to our Asian partners and companies there, why is it working out there and not with us in our case?
Thank you for the question. I mean, there's no way why there is no reason why it should not work for us as well. I think the main competitive advantage for them is that they have somewhat recognized early on the importance of this value chain, and they sort of have a sort of early market entry kind of advantage, having long established a full industrial ecosystem right around the rare earth recycling system industry, which includes both recycling, but also the permanent magnets manufacturing stage, but also a refining stage as well. If you remember from one of the first slides that I showed, they actually are quite strong also at the permanent magnets manufacturing stage itself, and that's telling because, of course, also in terms of skills, some of the skills required at different stages, some more overlaps. So that's, I think, the main elements that makes the sort of the difference. And then, of course, they have a well-developed collection an efficient collection system, for instance, that we don't necessarily have in the EU, where we still, for instance, export large amount of end-of-life application in several cases. For instance, in conventional vehicles, still we export several of them. So as a whole, it's a mix of elements, but I think that one of the main things is that being able to provide a full industrial ecosystem around recycling is one of the main, I think, elements providing. Yeah.
Again, I mean, we are in the lucky position then to talk later to Lucas and also to Pierre, you know, representing companies in this field of established recycling business. Looking forward to hear their view then later on. But maybe we go on and I would like to invite you, Jürgen, to give us a bit an overview technologically, what is possible and where do we stand. And by the way, the questions that you add into the chat window and in the question window, we will pick up later on. These questions are not lost. But let's move on for now with Jürgen and yeah, recycling technologies for permanent magnets. Over to you, Jürgen.
Thank you, Roland, for this kind introduction. Something like that Eduardo already showed. I just want to stress it out. So there are different kinds of permanent magnets we are using today. Low performance ferrites and Alico, and high performance rare earth permanent magnets like samarium cobalt and neodymium iron boron. And on the right hand side, you can see the market share by value. So 50% of the market share is about sintered neodymium iron boron magnets, about 30% is ferrite, and then there is still some samarium cobalt. However, if we are discussing permanent magnet recycling, we only dealing with the neodymium iron boron system because the samarium cobalt market is so small, and also the ferrite market. Even so, in terms of volume, ferrite is higher than neodymium iron boron, but in terms of value, the ferrite material is quite cheap. And therefore, moreover, it only consists of, let's say, iron, strontium, and oxygen. So it's quite a cheap material. So we are always discussing about neodymium iron boron in terms of magnet recycling. Obviously, different kind of grades. However, it's always a system. And if you think about recycling, you need in a circular economy the whole recycling chain. So obviously, you are using primary material. This one is at the end of life disposed. It needs to be collected, somehow disassembled and reconditioned, alloyed, and the magnet needs to be produced and also used in new products. And for a sufficient recycling circular economy for Earth, all this chain needs to be linked and needs to be closed, basically. And today, I want to talk and I want to focus only on the reconditioning, alloying, and magnet producing part in this recycling chain. But also, what is also needed is sufficient collection and also disassembly, is because one needs the permanent magnet disassembled from the product to really have it in a good recycling technology. But this will be focused in the other talks today. Concerning the material we have for recycling, there might be different kind of materials and also different kind of technologies used for that. For instance, on the top end, we see oxides, we see grinding swarf during magnet production. It's a very heavy oxidized powder. We have huge chunks of magnets, for instance, from MRI machines or also wind. We have smaller magnets from EV, and we have very small magnets from electronic equipment, for instance. So all these material might need to be treated in a circular economy. So if we have a look on how magnets are produced right now from bottom up, we have the mining of the rare earths, and we produce rare earth concentrates, we separate them into oxides, then metallize it, make an alloy by strip casting, and finally makes a magnet. And if you think the other way around in terms of recycling, basically the easiest thing is to reuse the product again. However, if you think about industry, most likely it won't happen because you are pretty much stick by the magnetic grade you basically have at the end of life. And to make a business out of it, you will always have to deliver whatever kind of homogeneous specification, and basically to always get the same material and sell it to somebody else who do something else with the magnet most likely won't happen. And also to use this material in the very same application is also rather not likely, because we saw in the talk previously that, for instance, for wind, most material will come back in the late 30s, and specification of the wind turbines which are produced in the late 30s are different than the ones which are produced 20 years ago. So this doesn't match. So you have to do something about recycling, and there are different ways. They are called short and long loop recycling. On the short loop and functional recycling route, one stays within the alloy system of neodymium ion boron. So one is producing a powder for whatever kind of technology and can produce with that a permanent magnet. And there are different ways to do. So one can go to a remelting, for instance, by strip casting, or melt spinning for producing sintered magnets by strip casting, and polymer bonded magnets, for instance, by melt spinning. Or one can also skip the melting step and start by hydrogen processes. So the hydrogen will decompose the material, a powder will be produced, and this powder can be then used for the production of magnets. By the HD route, one can go to the sintering route, and by the HDDR, one can produce anisotropic permanent polymer bonded magnets. And on the other hand side, the long loop or element oxide recycling steps, here we go back to the very separated oxides and elements. So we have hydrometallurgical routes and also pyrometallurgical routes by leaching, by liquid phase processing, and also by gas phase extraction. We can separate the material and really recycle the pure rare earth elements. However, if we balance that in terms of recycling, we always have to ask ourselves, how do we rate our process and our product? And here I rated it in terms of performance, sustainability, and cost. So if you think about a magnet or a product, you might want to have a very high performance to a particular price, and maybe also a high sustainability, and you can't maximize all of these measures. So for instance, for the long loop recycling, when we go back to the very pure elements, basically we can reach the highest performance in terms of permanent magnets, because when you start from mining and end up with a 99.9% pure metal, or if you start from cycling and you end up with the very same metal grade, basically also the magnet can be produced similar. However, sustainability might be lower because there are several process steps involved here. When you stay within the short loop recycling, however, you stay in the system, as the sustainability is potentially highest. However, magnetic performance is limited to the magnetic performance of the end-of-life material. So this balance is always there in terms of the recycling. And here, only to compare this to this basic routes on a very broad scale. So by the element recycling, we can really use also grinding swarf with this heavily oxidized. We don't have any limitation in terms of chemical composition, and we can reach the highest magnetic properties possible. However, we need a large amount of chemicals, high energy consuming during the processes, and we need several process steps. Whereas the short loop recycling, we have little to no waste, low energy, which we need, very high sustainability. However, this process is not suited for contaminated material. And also, if we have mixed scrap, this process is very challenging. So to sum up here, I think in terms of industrial recycling, there will be always this coexistence of short and long loop recycling processes, because you will always have different end-of-life feedstocks, you will have different specification for the recycled product, and therefore you will need also different kind of technologies. So here, the last slide concerning results. On the left-hand side, you basically see a DMAC curve of an e-scooter in blue. So it's an e-scooter where we just dismantled the motor, we took out the magnets, measured the magnetic properties, and basically recycled other types of magnets to produce the specification of this e-scooter magnet. In principle, we targeted for the resonance and we overshoot slightly the coercivity. And the message was to show it also in a product. So on the right-hand side, you see the motor, which was tested by the primary magnet and also by the recycled magnet. And obviously, the motor is performing similar since magnetic properties are also similar. However, this is also important that people understand that also with recycling and also with short loop recycling, specification can be met, which are also necessary for primary products. On the left-hand side, on the bottom, you can see it for another technology, for polymer bonded magnets, for instance. Also here with 100% recycled powder, very same grades can be produced like powder from primary material. And in terms of the long loop recycling, here is shown a bioleaching process. So the idea is to use a bacteria which can selectively leach elements, and dependent on the type of material, rather if it's a powder or if it's a block or whatever kind of magnet, the leaching efficiency for different elements is varying. However, it is possible to get a very high concentration for certain elements if the magnet or the end-of-life material is in the right form, in this case, a very fine powder. So last but not least, why do the recycling? Basically, you can see it on the right-hand side. So this is a work concerning life cycle assessment of rare earth primary production compared to the recycling. And also the primary production on the left-hand side shows a quite large number gaps between the carbon dioxide equivalent and dependence of the boundary conditions the authors used. However, it is clear that for all the recycling processes, one ends up with very high benefit in terms of CO2 equivalent for permanent magnets. So with this, I like to shortly sum up. So I hope I could convince you that there are several recycling technologies. I didn't go into very much detail here because there are so many of them. However, I think that several of them will coexist in future because they are more or less dedicated to other types of end-of-life material, and also the products one will need. So the specification of the recycled product will be way different and can be used for different kind of application. Obviously, all this technology perform very well in terms of CO2 equivalent with respect to the primary production. With this, I'd like to thank you for your attention and looking forward to your questions.
Thank you very much, Jürgen. Are there already questions that refer to that particular presentation? Jenny, I don't think so, right? Let's wait for maybe a few more moments. I was quite impressed by that one. Maybe you can go back on your slide and this e-scooter application. So here this diagram, that says e-scooter. So here you describe basically the performance of an e-scooter motor using magnets made from primary raw materials versus those from recycled. And which recycling routes was applied in this application? Is it from the short loop or the long loop? Do you know?
No, yes. So first of all, it's true. So we compared different magnets. So the primary magnets we tested in the motor, and we recycled magnets, other magnets, which we tested also in the motor. We used a short loop recycling process, starting from strip casting in this case, and producing sintered magnets. So in principle, the block magnets we got from the e-scooter were also sintered magnets. So we stood in the very same production route, but we took a variety of end-of-life material, which we then put together in terms of chemistry and in terms of microstructure to then produce the magnetic specification, which we measured as end-of-life product. And in principle, you don't need a magnet performance. However, what you will need in a scooter is a motor performance. The motor need to perform similar than with primary material. And this we showed here by the induced voltage, which was produced by this magnets in terms in the motor.
And you showed the different types of magnet. Isn't a magnet a magnet? So what is the different routes you mentioned? The sintering, the strip casting, the decrypitation, and so forth. Maybe could you explain a bit? Maybe where the different short loop recycling approaches kind of differ. So that would, I think, be helpful to understand.
Yeah, so in principle, a magnet is not always a magnet. So when I showed in the beginning, we are talking about neodymium iron boron, but also here we have material which is only the neodymium iron boron system. We also have material which is mixed with polymers to produce polymer bond neodymium iron boron. We have sintered magnets dedicated for wind. They are totally different than sintered magnet dedicated for EV, for instance, because the machines are working at different operation temperatures.
Okay.
So not every neodymium iron boron magnet is similar, and they also need to be treated different. And like I said, so some of them might be better suited to go into hydrogen decrypitation. Some of them are better suited to go into melt spinning, and some of them are better suited to put a part again into rare earth elements and use these rare earth elements for the production of whatever type of product. However, for neodymium, praseodymium, dysprosium, and terbium, like everything is used in permanent magnets. So most likely a magnet will be produced if this one is separated into the elements.
So you have the alloy composition, you have the individual elements, and then how you shape it into an actual functional material can really depend on the route you take. Is it cast into, you mentioned the bonded magnets. You have these sintered magnets with different structure depending on the application. So it is a complex story, and will be very exciting to see how these recycling routes really will be implemented maybe in these different application fields. Thanks very much. Thanks very much, Jürgen. And I don't know, are there questions related to that particular talk? Jenny, can you see?
Yes, actually there is one question. Is it important to recognize that current end-of-life magnets have higher dysprosium, terbium loading than future magnets that also are being loaded with increased loading of cerium to drive magnet cost? Performance of magnet is being worked upon the magnet manufacturer, but the future cost of the recycled basket of rare earth elements will be of lesser value in the future compared to now.
Yes, it's true. So if the materials which were produced like 15 years ago had higher heavy rare earth content than the materials produced now. So nowadays, most likely technologies like grain boundary diffusion is used to reduce the heavy rare earth content. So basically the value of an older magnet with about 5 to 7% of heavies is a higher value than a material which we are producing now, which has like 1%, for instance. So this is an issue. One can also think about what type of end-of-life magnet do I have, and then what recycling process might be better suited. What can I do with this type of composition? It needs to be shown basically how this material will behave in the recycling. However, what's clear is also the cerium part. So I think it's in principle good if we also take cerium in the permanent magnets. Most likely the magnets will have lower performances due to the intrinsic properties of the cerium. However, the effort for the mining will be less because the cerium is mined anyway. It needs to be separated and stuff like that. However, we should use as much as possible of the material which is mined. Saying that, this material might be to be separated from other material in terms of short loop recycling. So in terms of long loop recycling, it might not be that much an issue, but in terms of short loop recycling, to have a mixture of cerium magnets with non-cerium containing magnets might deteriorate the magnetic properties too much. So here, there might be a separation of these types of materials might be necessary, and also labeling material product passes and stuff like that might help that in near future.
So when you say they are kind of mined together, I think you're referring to this picture, this concept of a basket, right? Each time you mine a rare earth, it actually comes with a pseudo rare earths that come out of the actual mining operation. And these days, there's not so many applications for cerium and maybe even lanthanum compared to neodymium, right? So as much as we can integrate these kinds of rare earth of lower value into magnetic applications would actually enable benefits, right? So
yeah, correct. So if we take like the global mining as a reference, we will have in our rare earth ores about 25 to 30% neodymium and praseodymium, and like the rest is most likely lanthanum and cerium, about 60 to 70%. And the percentage of dysprosium and terbium is quite scarce. So so if we make use of this rare earth basket, it might be good in terms of reducing the effort for mining, but it will bring also a challenge in terms of recycling, that's for sure.
Thanks very much, Jürgen. I think this is a perfect also connection to the next speaker. So the next two speakers actually. Now we've seen the enormous potential in terms of markets demand, the supply, the potential of the urban mine in terms of end-of-life products being available. We see the technology options that are there, the different routes we can go for the different types of magnets, different applications. So yeah, how can we scale it? How can we implement it, Pierre? Like you work for a recycling company and where you're kind of exposed to those end-of-life products containing these materials, and I'd love to hear your view on the potential of the urban mine.
Okay, thanks for this opportunity to explain what we are doing as a recycling company. Do you see the presentation? Is it okay?
Yes.
Okay. So a short introduction first on my company. Comet Group is a family-owned company located mainly in Belgium and also in France. And you see that you are 500 people working for this company with a turnover of 500 million euro. And we possess two shredders. One is the biggest one located in EU 27 with 7,000 horsepower. And then we possess more than 1 million tons of waste per year, and out of which 800,000 tons are metallic material. So what we are processing as a material feedstock, we are processing waste from end-of-life, from electric and electronic equipments, end-of-life vehicles, and also scraps, metallic scraps coming from scrap yards or demolition waste. So the process is through physical, mechanical recycling. So we have a first dismantling phase before shredding or sorting. Then you have magnetic separation and destruction, and then we have three waste fraction. So the first scrap that are sold to the steel industry, that is a motor company. Then we have the light shredder residues and the heavy shredder residues. And Comet Traitement, my company, was created to handle those post-shredder waste. Just one thing, if you speak about magnets, the magnets will follow the ferrous scrap because the magnetic separation. So they are lost today in destruction if you don't dismantle. So dismantling to valorize the magnets is very important. So considering Comet Traitement, so the post-shredding valorization, The idea behind the company is to sort and purify the material to obtain secondary raw material as close as possible as the virgin ones. So to increase the value of the material. And if you see the valorization with the valorization rate for an end-of-life car, we process with different technology, mechanical sorting, and then more complicated, I will explain in a few words. So we get technical sand, we get plastics, we can be able to sort the different plastic and to get, for example, purified polypropylene ABS that we can re-enter into the value chain. We have also developed technologies. We are very active in research to develop pyrolysis, for example, for the ultimate lightweight like foams. And for the non-ferrous metals, we have developed many technologies like robotized sorting and hydrometallurgical processes. And then with this, we are able to recover critical raw materials or metallic materials purified, including rare earth. I will explain now. We are facing also new feedstock, and we are targeting those feedstocks. So the new feedstock are the end-of-life electric vehicles, also the light electric vehicles like e-scooters and e-bikes. And we are also investigating a new waste feedstock like end-of-life PV photovoltaic panels. We are also entering slowly in the aircraft recycling and also the windmills. It means also that we will face also difficulties like the fire hazards that are coming with the batteries. So the idea is always to be able to recover not only one material, but to have technologies considering all the materials that are present in the end of life, for example, e-scooter here. So we have the structural part with the aluminum that we can valorize. With the electronic components, we have developed also technologies to recover, for example, copper or different elements. The batteries, we have our research activities like all recyclers in this field to valorize different critical raw materials inside the plastic parts, and of course the electric motor where you find copper and rare earth elements. So where we can find rare earth elements in the end-of-life vehicles, of course, in the traction motors, in the e-bikes and the e-scooters, and then in the waste from electric and electronic equipments. So where you will find small magnets, not all containing CRM rare earth elements. So some of them are containing rare earth elements. And so you can find it in speaker, hard disk drive, laptops, but also sometimes in batteries like nickel, metal, hydride batteries. So those kind of object and rare earth element valorization is still under research activities at Comet. So for the valorization, for the electric vehicles and the light mobility, the main step is to extract the rotor from the electric motors. Not so obvious and takes time. Then extract the magnet from the rotors and then demagnetize the magnet. And okay, for the waste from electric and electronic equipment, the first step is to sort the component and then to dismantle the magnets that are not so big and it's not so easy to find, and then to demagnetize. If we don't do this, the magnets will be lost in the bulk material and not valorized. That's the difficulty. What are the challenges for a recycling company like Comet? First, it's where to find the magnets. and especially with neodymium and dysprosium and so on. What is the composition in terms of the neodymium? What are the amounts? And so we have to build an inventory, and that's what we are doing now, in particular in the Magellan project. And for example, even if you have an electric vehicle, you can find motors with non-permanent magnets, or ferritic or induction motors. So that's surprising, but it's not so obvious that you have permanent magnets with rare earth elements in all electric vehicles. That's one thing we have seen. Then dismantling cost versus market price. So the idea is to sell the magnet if you dismantle it. But if you take an example, if you take one end-of-life vehicle, you have a second-hand market where you can sell the end-of-life vehicle at something like 1,000 euros. If you take only the magnets, it's 40 euros. So it's not profitable. And so you should, as a recycler, consider not only the magnets, but all the different material that you have in the vehicle in this example. So valorize the aluminum, the steel, the plastic, and so on, to expect to have a positive value at the end. So of course, you can improve the cost and decrease the cost if you are able to automate the process and to have less, let's say, a costly operation. A third challenge is the critical mass. What will we do with the magnets if we recover magnets with rare earth elements? So we have a lab scale hydrometallurgical process to recover rare earth elements. But if we invest in a pilot or a plant, we need tons of magnets, and we don't have such tons of magnets. So the second option is to provide those magnets we get from our waste to a company, but there's no today very well known or a single company that is already active in Europe to process those magnets. So, but probably this option will be the most interesting for us. Traceability could support our inventory issue. But don't forget that the waste you are operating today, if we expect to have labeling, we have a delay time of 10 years before seeing labeling in our waste. Okay, and that was the message for me.
Thank you, Pierre. Thank you very much. It was a good kind of reality check. How is kind of the recycling situation of magnets today? How is it kind of showing up in those end of life streams? Now let's have a look at the Q&A box. Are there any questions, any comments related to this particular topic?
At the moment, there's no questions for this presentation.
Please, but you know, if you think about reflect about what has been said, please continue to add questions. We can then also at the end of the presentations revisit the individual.
Roland, now we have few questions here, so maybe I can ask. Would product passport help Comet activities?
What could the passport, the digital passport, help Comet? That's the question.
Yes, would product passports help Comet activities?
Maybe, but not today. Not today. And don't forget also that we are processing damaged products and various very different products waste. So digital passport, okay, could be efficient, for example, in end-of-life electric cars, but in small electric and electronic equipments, I fear that it won't be so useful.
And I think you were referring to the time delay. So everything that we implement now,
Yes.
of course, will also have only the impact at the end of the life cycle of the product.
Yes. Yes.
I'm not so worried because you only have a lifetime of maybe 4 years. But when we talk about the big volumes, the wind turbines, I mean, wind turbines are easy anyway because it should be clear what the technology is inside. But any other, let's say, industrial motor or other application is more complicated because they have a longer lifetime, right? And it will take time until they come back to your premises, right? And your recycling capacity. So, but overall, would you think that labeling would help? Like, would it kind of, if you had products that are, labeled, would that facilitate your day-to-day job?
Yes, probably, yes. So, but how to handle those labeling inside our processes, I don't know. We have time because you should have, let's say, digital systems, so smart tools to recognize the labeling and so on. But it's not a big difficulty, I think.
Any other more questions coming or?
Yes, there is one more. What about the challenges with aviation recycling?
This is not the rare earth elements. So in aviation, you have metallic content, so we are quite comfortable with those kind of waste. You could have also, and then you have composites. And composite is less, let's say, friendly regarding recycling, let's say. And so, but it is an issue is to recover also the carbon fibers and so on in the aviation. And we are working on this.
Any maybe last question and then we can move on.
There is one question that would dismantling instructions help Comet, as some of the magnets are sometimes hard to recover?
I don't hear why.
Dismantling instructions. Dismantling instructions to kind of regain the magnets from the.
Eco-design could help if, for example, in Magellan, we have this aspect to help to, let's say, dismantle and to recover the magnets. This will, of course, have some importance for us. Yes, of course.
Okay. And I see a comment here. How do I reach you? I'm interested in your magnet material. I take this as a question that I wanted to ask you. Do you make money today out of magnets recovery? And
No, not yet, because we are starting activities on this. And let's say that most of the magnets are small magnets. We have not so many end-of-life electric vehicles today. So most of the magnets are inside the waste from electric and electronic equipment. So we don't make money today, but it will be complementary to, let's say, the full package of recovery of aluminium, metallic frame, and so on. So it will be an added value.
Yeah, thanks very much, Pierre. I think that's the perfect also bridge to a last speaker, Lucas. You are COO at a company called Battery Lifecycle Company. How does that fit to magnets?
Yeah, I mean, so I'm happy to be here, and we had the discussion before why we named ourselves the Battery Lifecycle Company. We take care of batteries and treat these ones, and we figured out that the steps of dismantling a battery are similar to steps to dismantle a magnet or receive it out of the motor, which comes from a car. And therefore, we decided to increase our field of activity to the full drivetrain, which contains the battery, of course, plus the motor, which contains the magnets. And that's why we decided to move in that field. But I'll tell you something about it during my presentation. So just give me a second. So
Still loading, but
it is.
The slides are still, we don't see them yet, but I see that it is kind of there's something in progress here.
Okay.
But we don't see them yet, yeah? Maybe you can try.
Let me try it again. Just give me a second. Oh yeah, that's a good start. Having the system broken. Okay, just give it a second try. Okay, do you see it right now?
Yes, excellent. Thank you. Go ahead.
Okay, great. So sorry for that inconvenience in the beginning. My name is Lukas Brendel. I am the CEO of, or one of the CEOs of the BLC, the Battery Lifecycle Company. And we are a joint venture of two big companies. On one side, we do have the Rhenus Automotive, which is a company coming from the field of logistics, transporting goods from A to B, offering assembly solutions to their customers. So they are assembling corner modules, full vehicles for almost all OEMs which are active on the market. So they do have a very deep experience in assembling, in setting up serial processes for their customers. And on the other hand, we do have the TSR, which is a shareholder of the BLC, which is a big metal recycling company located in Germany, but also having facilities in France, Belgium, Netherlands, Austria, Poland, and Czech Republic. And these guys are very good to collect waste material, to treat the waste material and extract all the different kinds of material streams out of it. And with these both companies, we decided to fill up the field in between them, which means we're taking care of the after-sales market, or let's say everything which contains a product from the moment when it comes from the production facility till the moment the streams come in the final recycling. And that means receiving product output or production scrap, but also material which comes from the user or from garages or other parts where the material is collected. We heard a lot about magnets before. We heard a lot about the technology, about the possible streams and the recycling in the future. But I want to stress out in the beginning the car as an urban mine and how it is on the market at the moment. Because most of the cars which we see on the streets and then on the car dismantling yards at the moment are typical ICE cars. So there we still have a high volume of cars which contain a lot of steel, a lot of aluminum, copper, and other parts, and are fed into let's say a conventional recycling stream by collecting these ones, by dismantling them, and then bringing all the parts into the correct recycling to receive high valuable recycling goods out of it, which should ideally go in the end into the production of new vehicles by increasing the recycling content. The second stream with the cars at the moment and with the electric vehicles as well is a spare part stream. So if a car goes to the car dismantling company and they do the dismantling, they will decide which parts are still good to reuse them and bring them on in a spare part loop, and which parts are not good anymore and should go into the final recycling routes. And that is on one hand very good from an environmental perspective, but on the other hand, Pierre also mentioned it, it could harm a little bit the topic of the recycling, because you see less of the good material at the moment because it goes back into the material loop or in the part loop as a spare part. With a battery electric vehicle, we can increase the loop with the batteries, of course. they are totally new to the industry. So in the past, we had a lot of lead acid batteries, which were used for starting the car or running your electronic parts in the vehicle. But now with a battery, we have a part inside of it, which has a weight between 500 and 700 kilogram, which is totally new to the industry and forces everybody along the recycling supply chain to rethink his processes and transform the processes themselves as well by taking more care of the battery because of the danger and fire safety, but also by rethinking concepts of second life and spare parts as well. And then the second, let's say, new product is a motor or the drivetrain containing a bigger electric motor as we had it in the past. So in the past, we had electric motors inside of your window. We had some electric motors for your wipers, but all of them just had a weight of around 1 to 2 kilogram, and the new electric motors for your vehicles have a weight of around 100 kilogram. So the stream itself changed during the last years and is changing right now to the electric vehicles. How does it look like and how do we do it right now? We're partnering up with several car dismantling companies, and they extract the electromotors and rotors for us. So we're receiving these parts here. And then we do a manual extraction by opening the front covers and extract the rotors out of it. And the rotors contain the rare earth magnets you see here on the right side in this star-shaped line inside of the rotor. That is on one hand good because you see the material already to extract it, but on the other hand, that brings a challenge because the design of the rotor is different from OEM to OEM and is different from type to type. So you can buy an electric motor for vehicle type number 1 from one manufacturer, and then you can buy a second one, and they look totally different. And that makes it very challenging for everybody in the supply chain to set up automated processes to extract the magnets out of the rotors. But these are challenges we are working on to solve them in the future. With that knowledge of the extraction of the rotors and the extraction of the magnets, we call ourselves and we call that part of the supply chain the pretreatment, because the final recycling regarding the resources will be done by other ones who run the high volume facilities for magnets or for other parts coming from the dismantling. So there are other companies or parts of our company which are specialized in aluminium, other ones are specialized in copper to extract these good materials out of the stream. But for that, it's necessary to do the pre-treatment, which is done at the moment manually and should be done in the future automated to increase efficiency and decrease the prices to extract the material. And then we do have the topic of repair and spare parts, plus the so-called remanufacturing, which is very important from my opinion as well. As I told you in the beginning, at the moment, most of the motors which come from electric vehicles don't go in the recycling. They were extracted at the car dismantling companies or at the garages, and then they go directly in the spare part business. Because they are still good and they prove that an electric motor has a longer lifespan and a very good lifespan compared to a combustion engine and can be reused again if it's necessary and if someone has a need for it because his one is damaged by an accident or something else. But we see some challenges which are upcoming there. So Pierre ended his presentation with 4 challenges as well. I took the same number of challenges. The first one for me is the pickup of the motors and rotors to collect them and bring them to one collection hub where they can be treated, because they have a weight of around 100 to 150 kilogram. And it is a very high effort to pick them up at several places, at several garages to fill the stock and fill machines which are able to do the dismantling. Second one is the regulations. There are some discussions about the recycling content inside of the rotor. So OEMs are forced in the future to bring the material back into the loop. But also there are regulations which mean that the material should go back into the market as a spare part. And we see that a lot of cars are going out of the European market as well at the moment, and are shipped to other regions in the world. Third one is a variance. To increase the efficiency, we need to increase the grade of automation. At the moment, most of the steps are done manually, but in the future, they need to be done by machines. And the high variance is a challenge which needs to be solved to increase the recycling efficiency and to increase the recycling rate of the motors, and develop machines which can do it for you. And last but not least, we do have the information exchange, which could be a label, which could be dismantling manuals provided by the OEM or by the producers and manufacturers, just to have the information in which parts of the car, in which motors we can find rare earth magnets, and where it's maybe not necessary to do the dismantling because there are ferrite magnets inside which are less interesting for the industry at the moment. Thank you very much.
Thank you, Lucas. So exciting to learn about this new company being formed. So despite the title, you say you extend your work focus onto the entire drivetrain, which totally makes sense, right? And maybe one of my first questions before we look if we received other questions from the audience. Do you see kind of parallels? You know, if you look at the motor and the magnets therein, and how you can kind of valorize those materials to other recycling schemes. You know, I mean, when I think about automotive, of course, I think about the steel that is, you know, that is kind of recycled, or the copper that's been taken out, the electronics, or even with the electric vehicles, actual battery, right? So do you see things we can learn maybe from other areas of recycling in that particular sector?
Yes, of course. And I think the battery is one of the best examples for it, because it's a new stream coming in at the moment as well. But I would say the industry is more adult in that stream. So there are already ways to close the loop on an industrial scale, and to work with that stream. And you have not just one partner who is doing the recycling. It shows us, and that is similar to the magnet recycling, that you need a lot of companies and partners along the supply chain who can support that topic with their knowledge, with their technology, and in the end provide the recycled material back to the producer. And that is similar from the battery to the magnets. One difference is that the stream from a mass perspective, so from the weight perspective, is a little bit different. So you have 700 kilograms of a battery towards, if you take the motor 100 kilogram, or if you just take the magnets, you are at 1 to 5 kilogram of magnets coming out of one of these motors.
It's different length scales we're talking about. So and of course, big difference. Yeah. Okay, Jenny, are there questions coming in for that particular talk?
Yes, there is one question regarding variants in EV motor rotor design. Do you anticipate any converge in design to help mitigate recycling challenges, or is this issue likely to persist?
So I would be happy to help the industry in this field by discussing about design for circularity or design for recycling. That is what we do from time to time together with our partners. But it's similar to the development with a label. It takes a long time until the material which will reach us in the future. It is very important to start these discussions and increase the information exchange between all the participants. But the use will be there in, let's say, 8 to 10 years.
Okay, so I mean, material still needs to come back. The industry is growing, but it's, I guess, now that we talk about those topics, right? It's now that we talk about those standards. It's now that we need to talk about whether it makes sense to label or not, because we're at this growth period of electromobility coming in, right? And with this dramatic disruptive change in materials we're dealing with, right? So I think that the point you're making is quite strong to say we need to have this kind of feedback loop now, and the experience that you make in actually handling these materials, right?
Yep. So totally agree with you. And I don't want to say that it's bad to do it right now. I want to say it's necessary to do it right now, and that we should do it as quick as possible. Because of having this delay in the lifespan of the product, which is good as well, that the products are for a long time on the market. But what we missed in the past should be done as quick as possible to use it in the future.
Yeah. And in this context, just to mention that we are actually in touch with the European Commission on this topic and labeling, but also standardization in the context of sustainability, and is actually currently being worked on. So let's follow up, Lucas, and of course whoever is interested in that topic. There is actually an outreach happening currently by the Commission and by policymaking colleagues. We've seen this happening in the past few years, particularly in the field of batteries. You think about the battery directive that's been published in the last years, but we will see a greater impact also in other materials, and particularly rare earth coming more onto the stage now. Yeah. Okay, thanks very much, Lucas. Now I'm looking at Jenny. We've been through all the presentations. Maybe we can see if there are other questions in the question box that maybe also relate to the previous talks, and then let's see.
Yes, there's a few questions. First of all is Helena Robert, thanks for a lot for the presentation. Looks like it was a thorough research process. Could you please explain a bit about the profile of experts consulted? And Helena is from CIRAN, from LPRC, CIRAN EU project. So I think this is for Eduardo.
Yeah, I guess that might be referring to my presentations. In terms of experts, first of all, we could rely on a quite substantial base of knowledge within the project itself, right? And the project covered the whole value chain of magnets. We had manufacturers, we had recyclers, we had also the manufacturers of the final appliances potentially using the recycled magnets. So already there we could really get insights from all the different stages. But then we expanded as well, and we went beyond the circle of the project, and we consulted both academic experts from university that had looked into this as well, but also again from the industry, also more upstream segments as well. We also talked with potentially the mining industry as well, but also refiners and stuff. So overall, I think we included I think the numbers are in the report, but somewhere around 20 experts overall. For the research.
Then we had a question during the first presentation that how to set recycling targets if end-of-life products will only be available years later.
To Mr. Director, can you repeat the question, maybe?
Okay, yeah. So how to set recycling targets if end-of-life products will only be available years later?
Yeah, so recycling targets, we know in the Critical Raw Materials Act is actually addressing recycling targets, but these are global targets, right? Applied to across various value chains. And I think that's on the one hand a strength in the sense of bringing it up, making people aware of that. At the same time, if you apply those targets across various value chains, you end up in the challenging situation that in some areas we actually have already achieved those targets, in some value chains, in others we are light years away from those targets. So I think there has to be a differentiation and a differentiation of these targets to specific value chains. How can we achieve that if these big volumes are yet to come, right? I think that is a big challenge. Eduardo, any view on that?
No, yeah, that's I very much agree on what you said. I mean, the overall sort of benchmark target there at 25%, it is indeed also somewhat of an aspirational target there, right? That should also signal the political intention to really back recycling there. But as far as I know, the Commission itself will, not entirely, can't remember exactly the timeline there, but there will be a little bit more of a detailed sort of planning there in terms of targets specifically for the specific waste streams and potentially material, and that is also why we need this sort of assessment to understand a little bit where these material are in the first place and how long will they be in circulation in the form of waste streams and stuff. So that's why actually these assessments are needed to inform policymakers in setting targets. That is my take on that.
Any more questions in the list coming in?
Yeah, we have still a few more questions. How China deals with these challenges that other countries are facing to be the largest producer of rare earth elements? Other countries can't learn the Chinese processing technology.
So basically, can we learn, right, from the market leader here, which at least in terms of volume, China has become the leader here. That's crystal clear. So are there things we can learn or let's say apply best practices? I don't know if you with your activities are exposed to Chinese customers or partners. Yeah. Okay. That is actually it's a very good question, and I think also a good opportunity to learn and look into different areas. Now we see a lot of development in China for many years, but we also see a development in the US with the market picking up the topic of urban mining, circular economy of magnetic materials, and we have a very long tradition in the Japanese industrial ecosystem in that context, right? So there is, I think, a lot to learn for an industry that is in Europe at least is in a junior stage, I guess, right? In handling these larger volumes of materials. Yeah. Now I have a question also to both recycling companies, Pia and Lucas. Today, if you look at electric vehicles, by far most of these, let's say not electric vehicles, but let's say cars as automotive, the sector in general and cars, most of these cars are leaving Europe at the end of the life, right? They're traded worldwide. So for a second, third, or fourth life. So how do you see this impacting a European circular economy of these materials, and how can we change that? What is your view on that? Do you face this problem, this issue?
Yes, of course. It could be also the same for the wind turbines, where you have magnets, amount of magnets is 2,000 kilos, I don't know, of magnets and there are traders that so we haven't access to the magnets inside the wind turbines because they are sold to, I guess, to China, or let's say, I don't know, So there are regulation now. So the new LV proposal, directive proposal from the Commission, try to address this problem to, let's say, set rules to avoid exportation of waste or of end-of-life cars and so on. So European regulation could support recyclers, European recyclers, yes.
So the scrap actually has...
And at the same time, to imposing recycled content will also help, because we should keep those materials inside Europe.
So the scrap really, the end-of-life products really have a value, and they are today in many cases lost from our European ecosystem. So this is where regulation needs to kick in from your point of view. Okay, Lucas, any
Yes.
here?
I think there will be a change in the future with the battery electric vehicles. So we have at the moment the stream containing just ICE vehicles, or almost just ICE vehicles, and there we see that they are fading out of the. I see it from the German perspective, out of the German market, with around 60 to 80% of the cars are moving out of the market or are being disassembled illegally by someone who's doing it in his backyard. With a battery directive, with a battery electric vehicle, that will change, because it's not that easy to disassemble a car in your backyard anymore. It's more dangerous. You need more skills. You need other machines in the future to find out if parts are good or not. It's becoming more and more electric or electronic, and therefore I think the stream coming from the battery electric vehicles will be higher. That means higher recycling rates, and that means the recycling industry can provide more recycled material to the OEM and manufacturers who produce cars, including recycled content. But for that also the legislation is very, very important, that from the law perspective, someone tells the people, okay, you need to keep the material inside of the continent or inside of your region, and it needs to be processed there to have the material in the end for the recycled content.
Yeah, so basically this disruptive change in terms of automotive technology will have its impact not only in the use phase, also in the recycling, the materials we can extract, and how the waste streams evolve, right, going forward. Now, question coming back to Jürgen and looking at the technology that is so much needed to really process these materials. So why is it so difficult to handle these materials? I mean, rare earth, and also rare earth magnet materials. And do you see that we have the know-how in Europe, let's say the R&D and innovation know-how, and maybe even the know-how to industrially scale it?
Yeah, so first of all, I think why it's not done so far in a large scale, it's because of the supply and demand situation. It was already shown today that most of the material is not at the end of life and it's not there. So if you set up a business, you need a lot of stable supply of end-of-life material, which might be one of the largest problems at the moment. In terms of technology, I think that we are in a stage that there is still some technology in Europe. It's ramping up at the moment on also at universities and research organizations, but also startups and other companies are now going into the rare earth market sector, because it's just an emerging sector where we need at least some independence in Europe. So I see there a problem in terms of the time scale. If you think about what we need to meet the criteria of the Critical Raw Materials Act in 5 years of time, let's say, I think it was also shown by Eduardo in his talks that we have about 8 to 19% of recycled material by the year 2030, which might be too less. That's one point. And if you think about the recycling technologies, for instance, it really needs to be shown which one will come to the market and stay at the market first in terms of applications, like I showed. However, if you think about the whole value chain, there are it's very complex. So people who are, for instance, producing oxides are not also the people who are producing the metal, and it's also different companies who are producing the magnets. So the whole value chain is quite diversified, and not all of the steps are economic on the very same level. So, for instance, the metal making I see is really a bottleneck in Europe. If you can separate end of life magnets by leaching, for instance, you can produce very high oxides in terms of purity. However, you need to make a metal out of them, and this might be not that much lucrative because you are using a lot of energy for doing that. However, if you want to have a circular economy which is closed, then you also need these steps. And if I see the talk from Lucas, I think it's very great. We need that we dismantle end of life motors, for instance. But I think if we really want to scale this in Europe, the level of automation needs to be very high, since we can't afford so much money basically to dismantle this material, because even so, the magnet basically is moving the car, but it's about 3 kilograms of magnet which is moving the car with 700 kilograms of batteries.
Which is actually impressive, isn't it? I mean, it is the power and the power of this material, the functionality of these high energy density permanent magnets, and no, it's really fascinating. So it's really the integration of the different value chains, the profitability of each step of the value chain, and how we can approach that kind of a complete, how we can cover the full value chain here, right, and make it work. Thanks very much, and we're coming to an end. Thanks to all the speakers. Thanks to you listening and bringing up the good questions. I would like to close here, thanking again to the speakers, and highlight that in December 12th, we will have an in-person workshop at the Raw Materials Week in Brussels, fully focusing on permanent magnet materials, on rare earth, on the circular economy of magnets. So check this out. You can find all information in the web. Go to you can type Raw Materials Week Brussels, and you will see an exciting week of raw materials related events. And the most exciting day is December 12th, where we'll deep dive into rare earth magnet materials and looking into the entire industry. Thank you very much, and stay tuned. Thank you. Bye-bye.